Hello. Good morning. My name is Danny Shi. I'm with the Parallel Computing Platform team over at Microsoft in Redmond, and I'm happy. I'm excited to be here today to tell you a little bit about our plans for the future of parallel programming in .NET. Before I get started with the slides, I wanted to kind of kick this off with a demo. All right, so what we're seeing here is an application that's taking the live video stream data from my webcam here, and it's running a filter on that data, on each image that's coming in. And what the filter does is it returns a cartoon version of each image that's passing through. As the end result is we're seeing a cartoon version of me kind of messing around on the stage here. This demo makes use of a new technology that we have in CTP form called TPL Dataflow, and I'll be talking a lot more about TPL Dataflow later in the session, so I hope you're looking forward to hearing about it. All right, so before I get started, I have to mention some obligatory stuff. This talk is about the future. It's about technology that we have not released yet and may never actually ship. That said, we're doing the best we can. Almost everything that I'll talk about, though, is in CTP form right now. Some of it has actually CTP'd twice to be compatible with Visual Studio 2010 Service Pack 1. So you're free to try this stuff out and download it and make your own judgments regarding how usable it is, how consistent it is, and so forth. And we'd love to hear your feedback. Quick word about the agenda. I'm going to start by recapping the parallel programming support that we have already shipped in .NET 4. Just out of curiosity, could I get a show of hands regarding how many people are familiar with that functionality? So TPL, Task Parallel Library, plink, concurrent dictionary, concurrent asterisk, whatever. So all of that stuff is what I'm talking about. So I saw a lot of hands, that's cool, but not everyone raised their hand. That's fine, that's why I'm doing the recap. I just want to make sure that we all have the background knowledge we need to sort of understand the value of some of these future areas of work. And after the recap, I'll talk about two areas of future work. The first will be Visual Studio Async, and the second will be TPL Dataflow. All right, so recap of parallel programming in .NET Framework 4. There were basically three feature areas here. The first one was the Task Parallel Library, or TPL for short. Probably the most noticeable thing that TPL provided was these parallel loops. Basically, a developer could easily refactor his for or for each loops into a parallel for or parallel for each loop and kind of get some quick and easy performance gains on multi-core architectures. The other thing that TPL provided was a rich task library. Tasks allowed you to easily represent the asynchronous operations in your program. And one incredibly powerful feature with tasks was the ability to create continuations. Typically, continuation tasks were created by calling the continue with family of methods. And the idea was a continuation task wouldn't begin executing until another task completed executing. So it was this sort of handy way for you to asynchronously manage a chain of dependencies in your application. The second feature area was Parallel Link, or plink. Plink allowed you to just slap the asParallel method onto an existing linked objects query, and so make it execute in parallel. So it's very similar to the parallel loops in TPL in this regard, because it enabled you to get these really quick performance enhancements on multi-core chips with very little code change. With plink, it's not even really a line of additional code. It's just one extra method on the query. And lastly, we had this set of thread-safe data structures and synchronization primitives. Probably the most noticeable thing in this area was the thread-safe concurrent versions of well-known BCL collections. So concurrent queue, concurrent stack, concurrent dictionary. And the idea was you could create one of these things and party on it, access it, modify it in a multi-threaded way safely and efficiently. And the last thing that I pretty much always mention about the parallel programming support in .NET 4 is that it was pure libraries. Sure, there were language features that helped. One thing that comes to mind is being able to capture state via closure in C# and VB. But at the end of the day, what you were doing was calling methods and using types. And I think this is a good point to transition into the first area of future work, which is Visual Studio Async, or just Async for short. Async is a collaborative effort across both framework teams and language teams at Microsoft in order to improve the overall experience of asynchronous programming in the .NET framework. I'm not sure how many of you guys are planning on attending the Future of C# and VB session tomorrow. I think it's at like 2 or 3 o'clock. In that session, Alex will be talking about async the entire time, and he'll be focusing on it from a language perspective. So for example, how are the C# and Visual Basic languages evolving to make asynchronous programming better? In this talk, I'll spend about half the time, and I'll talk about it more from a framework perspective. So what new features are being added, how has the framework changed, and what's the collaboration like between the two teams to achieve this? All right, so to better understand the value of improved asynchronous programming in .NET, I think it helps to look at a few trends in today's applications. And the root trend that I want to point out is that applications are becoming more and more connected. I don't think anyone would deny this. It's more and more common for applications to make use of web services, to store data in the cloud, or to even offload general computation into the cloud. And what these things typically mean is more latency. The moment you begin talking about network communications, or the internet, which is basically just a really big, slow network, you're talking about orders of magnitude slower than accessing something on the local machine. And there are a lot of different ways to deal with latency. Unfortunately, I think given today's developer expertise for asynchronous programming and the support in frameworks and programming languages for asynchronous programming, latency is more often than not just kind of ignored, or it's dealt with in the wrong way. And what this typically means is UI responsiveness problems, scalability issues, and at the end of the day, you have unhappy user. So his application has stopped responding, he's trying to exit or kill it in the task manager, and in general, that's just a very frustrating experience, so it's a trend we are hoping to avoid. All right, so to see how we can improve asynchronous programming in .NET, let's take a look at what it's like in .NET today. So let's say I have a method, foo, that's synchronous and returns a T result. So foo is synchronous in the sense that when I call it, it's going to block and not return until it has done everything that it's supposed to do. What are my options? What patterns are available to me in .NET today to support an asynchronous version of this? One that I can call to kind of kick off the operation, and then go do my own thing, and then eventually come and join with the operation again. Well, one pattern that has existed since day one in .NET is the APM pattern, the asynchronous programming model. Some people call this the begin-end pattern. It has many names. The idea is if you want to implement an asynchronous version of foo, you write two methods. You write begin foo and end foo. Begin foo takes the same parameters as the synchronous foo method, along with a callback and some state. And so a consumer of your implementation would come and call begin foo to kick off the operation, and he gets back this iasync result object. Later, when he's ready, he can join with the operation by calling end foo and passing it the iasync result object that he got back from begin foo. And in this way, he could get the result of the operation. Another pattern that emerged, I think, in .NET 2 is the event-based asynchronous pattern, or the EAP. This one's really popular amongst the network APIs. And with this one, if you wanted to support an asynchronous version of foo, you wrote foo async. That, again, took the same parameters as the synchronous foo method. And then you would support a number of events that would trigger based on various stages of the operation. So at a minimum, you would probably have a completed event that would trigger when the operation completed. But more often than not, you would also have a faulted event or a canceled event for those respective states. And a consumer of your implementation would come along and call foo async to kick off the operation. Then he would subscribe to this various events that you've provided in order to be notified when his operation completed. These patterns were pretty good. They kind of served the purpose in the time they came out, but as we're finding asynchronous programming becoming more and more prevalent, we're finding more and more flaws with these patterns. For example, I'd ask you to consider this synchronous code written in .NET 4. After a few seconds, I think you can pretty much figure out what's going on here. It's just copying data from one source stream to a destination stream over and over again until there's no more data in the source stream. This is an expert's asynchronous code in .NET 4 using the APM. So basically, 4 lines of synchronous code became like 40 lines of asynchronous code. This code is hard to implement, takes an expert. It's hard to verify that it's correct, and it's hard to maintain moving forward. So that's definitely not ideal. Much better would be if your asynchronous code could look like this. The first time I saw this, it was pretty hard to kind of tell the difference between the two snippets, so I'll point them out on the slide. Essentially, you're seeing some new language features, an async keyword and an await keyword in C#. You're also seeing the methods returning tasks, and you're also seeing a convention change. All of the method names are being suffixed with the async word. So what's going on behind the scenes to support this? Well, again, there are language features. There's an async modifier which marks a method or a lambda as asynchronous. Basically, when you mark something async, you're giving the compiler permission to transform your code to make it execute asynchronously. And once you have marked something async, you're able to use the await operator within it. And what the await operator does is it yields control of the current thread until the thing you're awaiting, the awaited task, completes. And the framework has added a couple of new classes to sort of support these language features. They're pretty much all under the compiler services namespace. So the idea isn't for you to access these and use these straight up, even though they are public, but the idea is you would use these through the language features. So if we were to take a look at that code snippet on the previous slide, basically we're doing a couple things for you under the covers to support all this. When you mark something async, the compiler is generating some code such that a task can be returned from your method the moment you yield from it, the first time you use the await operator. So when you reach this code here, the await source.readAsync, a task is returned to the caller of your method such that he can monitor what's going on with the operation. And a continuation is set up on this operation, this readAsync operation. So it's much the same way that you would have scheduled a continuation in .NET 4 using continue with. When this operation eventually completes, the thread that got yielded because of the await comes back to execute the rest of the method, and this goes on, so on and so forth, through the loop. When the async operation finally completes, then the compiler runs some more code to complete the task that had been given back to your caller. So now he knows what the eventual status of the operation was, any exceptions it produced, and perhaps a result, if the operation produced a result. All right, so aside from kind of providing the underlying functionality behind the language features, what else has happened in the framework? Well, it should be obvious, but the task and task of T result types are now even more important than before. They're very central to this entire effort because they represent the ongoing operations that you would await and the ongoing operations that you would return from your asynchronous methods. And these ongoing operations could really be anything. It could be background work, could be async IO, so on and so forth. And the other advantage that tasks provide is a single object for eventual status of the operation, errors, exceptions, and of course the result of an operation. Also, the framework has added a number of sort of surrounding APIs to kind of round out the cast. I've got them listed here, but I'm not really going to go through these point by point because they're somewhat unrelated and that would be randomizing. But the idea is we kind of took a look at the use cases for the new asynchronous programming support. And we found the most common functionality and put it into the framework such that when you need it, you should be able to discover and find it in the right place. All right, so with all of that in place, with the new language features, the new role of tasks, and with all these surrounding APIs, we can add one more pattern to this list. We're calling it the task-based asynchronous pattern, or the TAP. So essentially, if you want to support an asynchronous version of foo, you write foo async and you return a task or a task of t result from it. And just to give you an idea of the kinds of APIs you may expect in a future version of .NET, here's a list of probably the most high-profile ones. This is by no means an exhaustive list. There's tons of work going on right now in many teams to support TAP versions of their operations as we speak. They're working on it. I just want to mention that the overall experience here is, let's say you're writing your application in .NET and you run into this synchronous operation that's blocking. It's taking too long, and you want to make it asynchronous. Hopefully, you'd be able to just find the TAP version of that operation and await it. And there you go. The code is asynchronous. So that's kind of like the ultimate vision of this entire effort. All right, so let me break out of the slides and do a quick demo. Okay, so it's not really too hard to explain this demo. Basically, a whole bunch of ants are crawling around on the grass, and when an ant gets too close to another ant, or he's on a collision path with another ant, he gets uncomfortable and tries to change his direction. In the writing of this demo, we ran into a pretty common UI problem. Basically, this ant simulation is going off on the background here, and we want the UI, the representation of all these ants on this bitmap, to be updated or to pull the ant simulation, but not too often. So if we look at the code for this, we have a simulation loop, an infinite loop here that always updates each of the ants on the UI. And conceptually, we wanted to wait like 50 milliseconds before doing it again to keep the UI responsive. So we basically wanted a thread.sleep here, but obviously that wouldn't work because this is the UI thread, so that would freeze the whole thing. So what we're doing instead is we're using a trick that's made possible with the new async support and one of the new APIs. So there's a new API delay that will be on task. It basically returns a task that won't complete until after a certain amount of time, so in this case 50 milliseconds, and then we're awaiting it. So what will happen is when the UI comes along and reaches this statement, the task here will not be completed, so it'll yield, and it can go do other stuff, and that results in keeping the UI responsive. When this task eventually completes after 50 milliseconds, the continuation that was scheduled here for the rest of the method runs, so the UI thread comes back and resumes the rest of the method, and this occurs over and over again. So this is just one example of how a very common UI problem, just kind of sleeping on the UI, is solved in a very straightforward manner by this new async support. And it's something that really wasn't that trivial to do previously in .NET. All right, so that's about it for what I'll say on async. Again, I encourage you, if you're interested in this, I encourage you to attend that session tomorrow where Alex will talk about this stuff. I think you'll have some bigger, flashier demos too. And I've also linked the CTP here. So again, please try it out. Give us your feedback. That's the reason we release CTPs. We hope to take your feedback and refine the product before we hopefully eventually ship it. Okay, so moving right along to TPL data flow. To understand where we're coming from with TPL data flow, I think we need to understand at a high level what parallel programming in .NET 4 was about. In .NET 4, when you did parallel programming, you were being very proactive in nature. Typically, you had the data already somehow, and then you decided what sort of computation to kind of do on the data. So for example, you had an array of something in memory, and you wanted to modify each element of the array very quickly. So you wrote a parallel for loop to do that. Or you wanted to filter this array, or join it with something else, or group it, or sort it, so you wrote a plink query to do that. And what we gave you to support these scenarios was basically primitives for task and data parallelism. But what was missing from the picture is the other side of the coin. The ability to set up the computation first and then react to the data when it arrives later. This paradigm, this model of doing things is often referred to as data flow parallelism because essentially you're creating this computational network through which data will eventually flow. And what we're intending to provide to support these scenarios is primitives for in-process message passing. These primitives are basically blocks that are capable of buffering and processing data. And they're often useful standalone, but they can also be linked together to create these aforementioned data flow networks. I should mention that none of this is the ideas for this aren't really new. Agents-based programming and message passing, that sort of thing, has decades of computer science research behind it. Also, there are related Microsoft technologies. So in the native world, there's the asynchronous agents library, which has already shipped in Visual C++ 2010. There's also the coordination concurrency runtime from the Microsoft robotics team. And my team even did an incubation project called Axum. What we're trying to do with TPL Dataflow is to take all of these great concepts from the research and from the prior art and make it something .NET ready. Put it in the framework such that all .NET developers can use it without any additional downloads or anything like that. All right, so let me get a little bit more concrete about what I meant by these blocks that could buffer and process data. So here is an action block. It's one of the new primitives that are in TPL Dataflow. So I've created an action block here, and I'm having it execute the process method for all input data elements, which in this case will be type integer. After I've constructed the action block, it kind of just sits there. It's set up its message queue, and it's not using any tasks, not using any threads, not hogging any resources when it doesn't need to. So the computational network, which in this case is really simple, has been set up. So all we need is the data, which can eventually come via the post method. As data gets posted to the action block, it enters the buffer, and the action block spins up a task to begin executing it, to begin processing the data. So here you have the buffering and the processing. And if more data arrives, while the action block is currently busy, then that data will get buffered until the action block can get around to processing them. When there's no more data, the action block spins down the task and goes back to just kind of waiting there quietly until more data arrives later, in which case it spins up the task again to get going again. The idea is there's a lot more where that came from. What you're seeing on this slide is the interface hierarchy of all Dataflow blocks in TPL Dataflow. So at the very top, you sort of have the king interface, iDataflow block. And underneath that, you have iSource block, which represents a source of data, iTarget block, which represents a target for data, and iPropagator block, which is both a target and a source. Given the methods on these interfaces, a source block can offer data or send messages to a target block, and of course a propagator block can both receive and send messages. With these interfaces, you're able to implement your own Dataflow blocks that would plug into any TPL Dataflow network, but we also provided a number of built-in blocks for what we think is the most common functionality. And these blocks kind of conveniently divide into three categories: buffering and propagation, executing, and joining. All right, so on the buffering and propagation front, the first block we have is buffer block. A buffer block's only purpose in life is to buffer data. It doesn't really do much in the way of processing. More specifically, it buffers an unlimited number of elements and delivers each element it has received to one target on the other side. Buffer blocks are really useful in producer-consumer scenarios where, let's say you have like a whole bunch of source blocks producing data and a whole bunch of target blocks that want to consume that data, and you need something to kind of coordinate the whole thing. You can have a buffer block in the middle that takes every element that's produced by the source blocks and makes sure that it's delivered to one target block. A write-once block in its lifetime only ever accepts one element, and it delivers this one element to all linked targets. So a write-once block is kind of like the equivalent of a constant in the TPL Dataflow world. And lastly, we have broadcast block. A broadcast block takes every input element it receives and broadcasts it to all targets. And of course, if more elements are arriving while it's broadcasting, it'll buffer until it's able to get around to them. So let's break out of the slides real quick and see if we can kind of cook up a small example that utilizes some of these blocks. So let me make sure this is big enough. If I begin typing off the screen or it's not big enough, someone shout at me and I'll try to fix the problem. So let's start with a broadcast block that will broadcast date-time objects. And I'll call this the time block. A broadcast block's constructor takes a cloning function, but if I don't want to clone the data, then I can just give this null. And who may be interested in these date-time updates, essentially? Well, this is a UI application, so I might as well print it somehow to the UI, and that's an action, so I can create an action block to do that. And I'll call this the UI block. Let's do this. And I'll have this be really simple. I'll just kind of overwrite the text on that huge button to the string representation of the date time. And I have to be kind of careful here because the button is a UI component that's affinitized to the UI thread. So I have to make sure that this action block only ever executes on the UI thread. And the way I can do that is I look on the other constructors of action block, and I see that one of them takes this execution data flow block options parameter. So I can construct one of these things, and I see that I can set a task scheduler property to task scheduler dot from current synchronization context. Basically, what's going to happen here is the action block will only ever execute its delegate on a task scheduler that will delegate to the current synchronization context at the time this method is called. The current synchronization context at that time will be the UI thread, so I have the behavior that I want. So now I've got my two blocks, so I can create my simple data flow network by linking the time block to the UI block. Now the data flow network, the computational network, has been set up. All I need is the data, which I can eventually provide by scheduling another task here. So I'll just have this task kind of repetitively push the current date time into the time block. But I don't want this to go too quickly because it's for demo purposes. So I'll use the same trick that I was using in the ants demo earlier and await a delay task. So this is a good example of how that new async support can not only be used with methods, but also with just random lambdas that you're declaring on the fly. So if I were to run this and click the button, I get the date time being posted to the UI with a responsive UI. So to move on to a slightly more practical example of this, let's go back to that ants demo. Now, if you were to think about how this demo may be implemented in a TPL data flow world where everything is being represented by these blocks, one way to do it is to represent each ant as a block. When an ant figures out where it wants to go next, it can broadcast that location update to all of the other ants. So it's kind of like the classic use case of a broadcast block. And if we look at the implementation, that's exactly what's happening. There is a broadcast block to which all of the ants will broadcast their state. In addition to broadcasting their state, an ant has to be able to react, to take action based on location updates from every other ant. So as you might expect, there's an action block within an ant block. And what the action block does is when an ant receives a location update from another ant, it figures out how far it is from the other ant and whether or not it's on a collision path, and it uses that information to perhaps influence where it's going to move next. And we're thinking that this will be a very powerful, nice pattern where you can create your own custom block. In this case, it's an ant block that implements one of those core interfaces. So in this case, iPropagator block. But you don't have to implement all of the block's functionality from scratch. You can make use of some of the built-in blocks. So in this case, an ant block's target side is an action block in order to react, to take action based on data that's coming in from the other ants. And the source side is a broadcast block, so it can broadcast its state updates to whoever is interested. That may be the other ants, that may be the UI. All right, so let's take a look at blocks that can execute code or logic based on incoming data. We've already seen action blocks several times now. An action block executes an action delegate for each input element. A transform block transforms each incoming element to an output element of potentially different type. And a transform block kind of introduces the concept of buffering on both sides of the block because it has to buffer on input until it's able to get around to processing the input, but it also has to buffer on output until another block is able to come along, and consume that data. And lastly, there's transform many block, which is related, except it transforms each incoming element into a collection of output elements of potentially different type. That collection could contain 0 elements, or it could contain a great many elements. So let's break out of the code again and see if we can update that example to include some of these new blocks. So let's say I'm not interested in the current date time. I'm interested in the time until some event. Let's just take PDC, for example, because PDC is cool and Microsoft always announces a whole bunch of new technologies there. So I can create a transform block that will transform date times into strings that will represent the amount of time remaining until PDC. So I'll call this the until PDC block. So I need to return a string, and I'll say time until PDC. And PDC this year, I believe I heard it's around mid-September, so like September 12th. And I'll subtract from this the date time that I'm getting passed and take the string representation of the entire thing. Now I'll change the UI block to take what the transform block produces, which is a string in this case. And that makes things simpler, so I can just set the button text to the string. And then I'll relink everything. So I'll link the time block to the until PDC block, and the until PDC block to the UI block. Now if I run this, I get the countdown until PDC with still responsive UI. So I'm seeing there's approximately 117 days, 13 hours, and 11 minutes until PDC. So again, to move on to a slightly more practical example, if you remember that webcam demo that I was showing very early on, the heart of this demo is a single transform block that transforms each incoming bitmap from the webcam into a cartoonized version of that bitmap. All right, so the last category of the built-in blocks are blocks that can join or batch data. So the first one we have here is batch block. A batch block groups multiple input elements of type T into a batch or an array of those elements. And all of the joining batching blocks support what we're calling greedy and non-greedy behavior. Essentially, to understand this, let's say I have a batch block that wants to create batches of size 10. As it's waiting to create those batches, it can either greedily grab messages and data from other blocks and kind of hoard them in itself until it has 10, in which case it produces the batch, or it can kind of politely wait until it knows it can get 10 from other blocks and then produce the batch then. So it's about where intermediate elements are being stored. And we believe there are different scenarios where you might want greedy or non-greedy behavior. A join block joins two input elements of potentially different type into a tuple of those two elements. And a batch join block is essentially the combination of the two as it joins two collections of input elements into a tuple of those collections. So one more time, let's kind of break out of the slides and see if we can update this demo one more time. Let's say there's another piece of data that kind of relies on the date time that I want to have here. Let's say it's my happiness. So I can create a transform block that again takes the date time and returns a string that represents my happiness. And I'll keep this really simple. I'll just have my happiness be dependent on whether or not the number of ticks is even. And I'll return a smiley face if it is even, a frowny if not. And the idea is my happiness could be correlated with the amount of time remaining until PDC. So I want to see these pieces of data next to each other so I can join them using a join block. Join block will join two strings. And now I'll update the UI block to take what the join block produces, which will be a tuple of the two strings. And I'll have the button text be updated to item 1 in the tuple, which will be the time until PDC, plus a new line, and then the second item, which will be the smiley face or the frowny face. And lastly, I'll relink the whole thing. So I'll have the time block linked to the until PDC block, but also to the happiness block. And I'll have the until PDC block linked to the first target of the join block, and the happiness block to the second target of the join block. And lastly, the join block to the UI block. Now if I run, I'm getting the countdown until PDC as well as the smiley, the frowny face. Because currently my happiness is dependent on something completely random, whether or not the number of ticks in the current datetime is even, it doesn't seem that there's much of a correlation here, but I'll tell you honestly, I'm really excited about PDC this year. All right, so I know that example that I was kind of writing on the fly wasn't the most serious practical example, but I hope you got the idea that there are a lot of these built-in blocks. And as you pick up this technology and begin using it in your scenarios, hopefully you'll be able to just kind of pick and choose the blocks that have the functionality that you desire. And it can even be kind of really fun in the process. And if the built-in blocks don't work for you, you always have the option to implement your own. Aside from the blocks themselves, there are also a number of options classes and extension methods and utility functions. The options allow you to tweak certain behaviors in the blocks. And there's a hierarchy to the options too, because certain options are only relevant for certain kinds of blocks. So if we look on the base class, Dataflow block options, we see task scheduler. This should be familiar if you're familiar with TPL and .NET 4. We already saw how this could be used to, for example, make sure that an action block only executes on the UI thread. There's also cancellation token, so you can cancel the activities of a block. And also bounded capacity. This one's really important. Basically, bounded capacity allows you to set a capacity, a bound, on the buffer of a Dataflow block. To see how this could be really key, let's take a look at that webcam demo one more time. So that transform block that's sort of in the middle of it all is being bounded such that its buffer will only ever have one bitmap. And the reason it's doing this is because the filter that's returning the cartoon version of the image is really slow compared to the rate of incoming data from the webcam. The rate of incoming data from the webcam is like 30 frames per second or more, depending on the webcam. And given the compute resources on my machine, just can't keep up. So if I were to change this back to infinity, which is the default, and run the demo, almost immediately the transform block is being sort of overwhelmed by the data. And so I'm getting a very historical view of what's going on in the world. So much better would be if we put it back to what it was originally, where it's bounding to 1. In this way, as soon as the transform block is finished executing or processing one image, it's able to pick up the very most recent image from the webcam. And that makes for a much more pleasant demo. All right, so one option that's specific to executing Dataflow blocks like action block is max degree of parallelism. So to see how this one might be used, let's look at this previous slide here. You'll note that when items get into the buffer of the action block, it spins up only one task to deal with those items. The reason we do this by default is we want to maintain some amount of order. We want to process messages in the order that they're received so that There's some fairness here. If that's not important for your scenario and you want to optimize for throughput in any way possible, then you can increase the max degree of parallelism option such that any of these executing blocks will spin up more tasks to deal with the data in the queue. And on the grouping data flow block options, we already saw what it means for a block like batch block or join block to be greedy. And aside from the options, there are a number of utility functions on the data flow block class. Most of these are handy in one way or another. The one I'll point out is toObservable or toObserver. Basically, these return iObservable or iObserver versions of data flow blocks such that you can play nicely with something like the reactive extensions. All right, so that's basically all I had to say about those two areas of future work. I've already mentioned this session, Dev 324, a couple times. If anything in async interested you, I highly encourage you to go to this session. It's at 3:15 tomorrow. Here are the links to the CDPs. If you were to only try one of the CDPs, I would download the VS Async one because that one contains TPL data flow too, but a much older version than is in the second CDP. And of course, the forums. So if you have any questions or you run into issues after trying this stuff, this will be the best place to get those questions answered. Of course, please fill out an evaluation. You can win some of these prizes, but more importantly, it makes speakers like me better for next time. And with that, I'm done, but it seems like I have a lot of time, so I'm happy to take questions if there are any. Yes? Sorry? Right now, the CDPs are implemented on top of .NET 4, but the eventual idea is for it to be in some future version. There is no current way, and there's probably no plan to do that either. Any other questions? Yeah. You need to specify a number, and it applies to the entire block. Basically, what it means is this block will spin up at maximum this many tasks to deal with the data in the queue. Does that make sense? Yes? Yes, they do. Yeah, they should be available either via the TechEd site, or if you want, I can send you a pointer later to them. Yes? Sorry? The bounded capacity and the... Oh, max degree of parallelism is the number of tasks that the block will spin up to deal with incoming data. Bounded capacity is the number of items that can be in its input queue. Does that make sense? I can clarify that later if you want. Oh, sorry? Right. Is there anything we can be doing with our code now to hopefully make it easy to refactor to that once it's actually shipped? That's a reasonable question. I would say that, in my opinion, the APIs in the CDP are already fairly mature in the way the language feature works and that sort of thing. Of course, there can be changes, but I think if your code builds against the CDP, you're in pretty good shape. That's my opinion, though, not a Microsoft statement. Yes? When you have a couple of blocks linked together, how do you control whether the output of one block goes to another? I mean, let's say you're running an operation where the first block, whatever you're operating on, is no longer eligible to go into the second block. Is there a way to control that, to cancel that one object from the pipeline? So what you're asking for is additional linking options, right? If a block is linked to many different blocks, how can you have better control over where messages will go. That is one feature area that we're thinking about. So if you have specific scenarios for that, I'd love to chat about it. Yeah, and that's another reason why you might want to tweak the greedy behavior of blocks, because that controls whether or not a block will steal that data away from another block and that sort of thing. Yeah.
Well, I'm thinking about an example of a state machine.
Mm-hmm.
Well, you're processing events, and this one state may not necessarily go to the next state, but it may transition to a different state, and then you might need to either jump one block, if you will, or maybe take out the object altogether from the entire pipeline.
Cool. Yeah. Thanks for the example, for sure. Yes.
For complex calculations in this environment, you might want to be able to have a graphic visualization of your block constraints. Do you visualize something like that for the IDE?
Yeah, there's been a lot of talk about that. You're talking about like debugger or even profiling support for networks like these, right? Right, it's definitely an interesting idea. I certainly wouldn't expect that for vNext, but yeah, I mean, but it's being talked about for sure. Yeah. Yes. Yeah, the await support is being planned, I'll say, for vNext of both C# and VB. Currently, those are the two most high priority languages, but the idea is to involve more and more languages as we move on.
Okay, so at the moment, how is it implemented, the language changes like that?
Oh, you mean when you download the CTP? It'll replace your compiler. Yeah, it is a new compiler, yeah. Yes. So you want to cancel an await operation?
Yeah, it's taking too long and I don't want to wait for it.
There is no way in the CTP, but that's very interesting. It's something we're thinking about. Again, if you have a scenario, I'd be very interested to hear about it. Any other questions? Yeah.
Take something compiled from CTP and run it on just info on it?
Oh, so take the CTP, compile the program, and run it on something that doesn't have the CTP? I have no idea if that will work. It depends on what you do, because the CTP provides compilers as well as new DLLs. If you build against those other new DLLs, then it's not going to work against something that's just .NET 4. However, I think it would be possible if you're only using the await support and not using any of the new APIs. You can do it, but there's no support for it. Yeah. Yes? vNext as opposed to vNext next. Yeah. That's correct. Yeah. Yes, that's the idea. There will be the big change in the framework for vNext that's being planned now is this entire async thing. Currently, you only have the CTP to play with. But I remember with Visual Studio 2010, the second beta or something was Go Live license or something like that. So it could occur sooner than you think.
What's the support for exception handling? Let's say these blocks, when they're processing the message, it gets an exception. I don't want it to go further. I want to take, for example, a different route.
Right. So each Dataflow block has a completion task. It's basically just a .NET 4 task. And when a block faults, you can access that task to get those exceptions. So you could also schedule a continuation on that task that would get fired when an exception happens, and so on and so forth. So the exception support in both the async stuff and in TPL Dataflow is actually really good. That's actually one of the main advantages of that I didn't really point out in the async support, is that with some of these previous patterns, like the APM, you had no idea what to do with exceptions. Most often, they would just tear down the process. Any other questions? Yes?
Can you use the balance capacity to like stop the whole thing until you get more capacity? Or just throw away the blocks that are
It will, you mean when you've bounded a block, right? It will not throw away messages. It will just reject messages when they're offered from the source. So the source will keep them unless another block that it's linked to will take them. So if you're only linked in a linear chain and you have a bound on one, you have the behavior you want, because the target block will just keep rejecting and the source will be like, keep offering until there's more space in the queue, in which case it'll actually do the transaction. So, yes? Right, so the linking dictates an implicit transfer that will happen when one source block, so when a source block is linked to a target block, then when the source block produces data that is ready, it will be offered to all of its target blocks. Yeah. So, yeah.
plans to integrate the data flow into the base, the BCL?
The plan is to put it into the .NET framework. I wouldn't say, I wouldn't really call it BCL, but close enough, my opinion, yeah. That stuff, if it makes it into the framework, would certainly be BCL because it's stream. Yeah. That's a good question. You know, I'll honestly tell you that we've run a whole bunch of perf tests, and it's pretty rare for increasing that max degree of parallelism option, the one that gives in-block parallelism, for that to provide benefit. Typically, your benefit is coming from the asynchrony of the many blocks executing. Does that make sense? Like if you have 5 or 8 blocks going, that'll do 8 cores of stuff, and you shouldn't need to introduce more parallelism within the block. But it's always a shady area there. You kind of just have to play with it and for whatever the application is and see what works best. Yeah. So I'm not sure if I have a recommendation either way, but if I were to lean one way, I would go for inter-block parallelism rather than intra-block parallelism. Right. Sure, so if you have identical blocks, then yeah, it makes perfect sense to have the parallelism within that block. I guess I was imagining, typically with these blocks, it's more heterogeneous, where you have a lot of different things happening. So, yeah. Cool, thanks. Any other questions? Yeah. Right, so the default task scheduler for Dataflow blocks is taskscheduler.default, which points to the thread pool. Yeah.
Would that same thing apply to, let's say, an ASP.NET application? Could I use the same blocks, etc.?
Sure. As long as it's .NET, you should be. TBL Dataflow is back to the library-only approach, so it's usable anywhere that that the framework is supported. Yeah. Any other questions? Yeah, sure.
When data flows through the blocks, it's supposed to decopy between each block, right?
So that's where we're getting to. If you remember, that broadcast block had a cloning function. Yeah, so you're either propagating references or you can clone and create a new object. But we wanted that option because it can become a performance bottleneck if you're deep copying and cloning without needing to. So, yeah. Cool. Anything else? Yeah.
What can you tell us about any attempts made to further simplify the syntax and complexity of parallel coding? My concern is that if my development team butcher if-then statements to really enhance the code, is there anything that can be done, when we start needing parallel processing to further simplify the bare necessities
Sure. It's definitely a reasonable request. Lowering the bar for parallelism is always the quest, the holy grail, basically. I would say the await support brings you very close to that. Because if you think about it, we keep pushing the async and await support as improving asynchronous programming, but asynchronous programming is like one short step away to parallelism. If you have multiple awaits, you have parallelism now. So if you have many blocking operations or process-intensive operations, if you're sprinkling awaits in your code, more often than not, that'll just start working in a way that starts utilizing all of your cores. TPL data flow would be, as you say, like one step more in advancement. It's talking about an alternate paradigm for a lot of problems that can already kind of be solved with the existing support. But yeah, definitely. We're not stopping with vNext or even vNext next with parallelism stuff. Right. Awesome. Yeah, we do have UX guys on it, so if you spot things that you think are just horribly named, then let us know, and I can give them that feedback, I guess, but thanks. Yeah. Communicating sequential processes? I'm not sure what that is. Yeah. Sorry, yeah. Any other questions? Yes. Could you use the mic or come up closer? I had trouble hearing. Or why don't you, yeah. What kind of interface?
Like where you're chaining your linking operations.
Sorry, could you repeat or clarify?
Like with link, if you're not using the SQL style syntax, you're just chaining.
Oh, I see. Are you talking about like implicit linking of the blocks, so you're not explicitly linking? Is that where you're going with this? Or?
Say you call a link to this block,
Mm-hmm.
then that method returns the block it's linked to, so that you can chain another link to call a block.
Oh, I see. Yeah. Yeah, we haven't really thought about that. I see, yeah. So you're talking about the link to returning the correct block such that you could easily syntactically link. Right, so if you have, right now the links return an iDisposable to dispose the link. Yeah, so you need to at least return that. But I mean, it's worth considering, like unlinking can always be handled via another means, yeah. Sure. Right. It's definitely something you can implement on top of it. If it's something important to you, though, definitely raise it. And yeah. Thanks. Yeah. Performance optimizations. There are. It's the work isn't done yet, but I'll tell you the state of the second CDP isn't one where they were just scrambling to get all the functionality in. There has been quite a lot of significant work on the performance front in both the async work and in TPL data flow. Yeah. So what that means is if you're using it, I would expect performance improvements between the CDP and if this eventually RTMs, but probably nothing too major. Yeah. Sure. No. It doesn't, it's functionally equivalent to await in that the next statement won't execute until the thing you're awaiting completes. So it's like you waited for the operation, but no thread is sitting there waiting, blocking. It's all being managed asynchronously such that when the operation completes, the thread comes back from somewhere else to execute the next line. you understand the difference? So like if I have operation A and I call wait on it, then the thread sits there until it finishes and it's hogged and it can't do anything else, and then it moves on to the next statement when A finishes. But if you await it, then the thread can go off and do other stuff, and the system is such that when A completes, the thread comes back to execute the next line. Right. Right. That's the whole idea, is to one major use case is to, if it's a very important thread, like the UI thread, you're freeing it to do the important stuff that it has to do. But the other issue is scalability, such that if you have a whole bunch of these blocking operations, like in a server setting, you're not having hundreds of threads just blocked on stuff all the time. You're having them constantly being reused for other stuff while operations are blocking. Yeah. Cool. Any other questions? Thank you guys for coming.